Guys, today we are going to talk about conservation of energy. So we're going to put all of these things we've been talking about in this unit together. So let's dive on in. So friendly reminder, you might have heard this before, but conservation of energy is very similar to the conservation of mass. The energy is not created or destroyed. It just changes what form that it's going through within a system. So I've got an example here. We've got Buffy throwing a water balloon at Biff. At the beginning, you'll notice our system is the Earth, the balloon, and Biff. Buffy's not in the system. So at the beginning, we've got the just gravitational energy because the balloon is up high. And then you'll see in the middle, we've got Buffy applying work to the balloon because she's not in our system. And then at the end, we've got kinetic energy because the balloon is moving. We've got gravitational energy because there's some height still above the ground because we're considering our point at 0 at the bottom. And then we've got thermal energy. So taking all of these pieces together, we could really come up with an equation. We could say gravitational energy plus work, which are these 2 points right here, gravitational energy and work. So those two add together. We've got 1, 2, 3, 4, 5, 6, 7. 7 boxes is going to be equal to our kinetic, 1, 2, plus gravitational, 3, 4, 5, plus thermal, 6, 7. This is not new. But this is really the basis for where we're going to start this conservation of energy. There were 7 boxes before, there's 7 boxes after. And now we dive into really a little bit more about how do we do calculations with these. I've got some examples. We're going to dive right on in. So let's get started. So our example 1, we've got a box of the mass of m sliding along a friction-free surface at 9.87 meters per second at a height of 1.8 meters. It travels down the hill, then up another hill. So we're going to start by figuring out what the speed is at the bottom of the hill. And sorry, my picture's a little off, but that's really fine. So looking at this, at the beginning, I have height, so I have a gravitational energy, and it's moving, so I have kinetic energy here. So that's our beginning. And then we want to know what's at the bottom of the hill. Our 0 reference line is going to be the bottom. So at the bottom, I just have kinetic energy. So for A, I'm going to have, to start with my equation, gravitational plus kinetic energy equals kinetic energy. Now, this is what I mean when I say write the equation. This is going to be our conservation of energy equation. Really, the conservation energy equation is that E initial is equal to our E final, but either one of these would work as a conservation of energy equation. And I'm going to go ahead and plug in the equations we've learned in the past couple lessons. Gravitational energy is mgh plus my kinetic energy 1/2 mv squared. And this v is our initial velocity because we're on the initial side. Equals 1/2 mv squared. And this would be final velocity. Now you'll notice here it gives me a block of mass m. But since the mass doesn't change, we can actually just start by canceling out the mass because it's in every single one of our items. Now, if the mass were to run into another object and then it would change, so it would change the mass of the system. But right now, the mass of the system remains the same, so we can cancel it out. So we can't cancel out g though, so I'm going to start with g. I'm going to use 9.8 times my height of 1.81 plus 1/2, and we know our initial velocity is 9.87 squared. And this is going to be equal to 1/2 final velocity squared. Now, right away, I'm just going to use my gut reaction and what I know in life. I know that if something goes down a hill, it's probably going to speed up. So I'm anticipating that final velocity is going to be greater than the initial velocity was. And I really want you guys to kind of do that while you're thinking through problems, thinking through like, what's going to happen? Am I expecting this number to get bigger or smaller? So on the left side of my equation, I plug it into my calculator and I get 66.45. And then we have 1/2 v squared, f squared. We're going to multiply each side by 2 to get that 1/2 to the other side, which gives me 132.89 equals vf squared. And then we just have to square root our answer. So if we square root our answer, we get a velocity final of 11.5 meters per second, which followed what we thought. We thought that it was going to speed up when it got to the bottom of the hill. Great. So the next question asks me to find the maximum vertical height to which the box will rise. And it means on the top of the hill. I kind of blocked it off. But we want to know how high up is this block going to go? So we want to know at the max height, our velocity is going to equal 0. So we want to take, okay, if this at the beginning is all gravitational plus kinetic, we want to know at the end when it's all gravitational, how high is it going to go? So we're going to do this. Now, you technically could use the bottom of the hill as your initial condition. I'm just not doing that because I have the numbers. And if I were uncertain in my answer for letter A, I'd probably want to use like my initial given information. So we can say gravitational plus kinetic is equal to gravitational. Now, this would be, again, the energy initial is going to be on the left side, the final energy is on the right side. So mgh plus 1/2 mv squared. Now this time, this h is the initial height, equals mgh, and this is our final height. Again, mass can cancel because the mass of the system doesn't really matter when we're talking about energy because it all cancels out. So 9.8 times my 1.81 plus 1/2 times my velocity, which is 9.87 squared, equals 9.8 times hf. And I plugged all of that in previously, the left side of the equation, which is where we got that 66.45 equals 9.8 hf. And then we just divide that answer by 9.8 to give us our height, which is a height of 6.8 meters. So I want you to stop and think to yourself, does that number make sense? Does it make sense that it would go up higher than I started? Because when the velocity is 0, all of that beginning energy that was gravitational and kinetic has now all changed to gravitational energy. You need to start thinking through these. Do these numbers make sense? Does it make sense that it would go higher when I don't have any velocity? Yeah. All right, let's do an example with some spring stuff. So I am blocking the picture now. Let me make myself smaller. There we go. A 66 kilogram trampoline artist jumps upward from the top of a platform with a vertical speed of 5.1 meters per second. How fast is he going as he lands on the trampoline 2 meters below? So we're not looking at the trampoline yet. So let's look at what types of energy do I have. At the beginning, he moves upwards. So if he's moving, we have kinetic energy. But he's above the ground, and I'm going to say my 0 reference line is here, even though, like, again, we can decide where 0 is. Even though we have a little bit of height, I'm going to say we have some, that's my 0 reference line. And then we want to know how fast is he moving as he lands on the trampoline. So I'm going to say it's all kinetic. This is like when that term just before he hits the ground comes into play, because we're not going to look at that spring energy yet. We will, though, on the next part. So part A asks how fast is he moving? So I want to say we know our energy initial is equal to our energy final. We have kinetic plus gravitational energy at the beginning, and then we have kinetic energy at the end. So 1/2 mvi squared plus mgh equals 1/2 mvf squared. Mass can cancel. Doesn't have to cancel. We have the mass provided, but I'm going to do less math since I don't have to use mass. The reason mass is provided on this is the next part, the mass won't cancel out. So I can say 1/2 times my 5.1 squared, because we know he's jumping up. It doesn't really matter if he's going up or down right now, because that velocity gets squared. And if he's going up at 5.1, when he comes back around and goes downward, like he goes up and then down, he comes up at 5.1. By the time he's coming down, it'd also be 5.1. So that number is not super important if it's positive or negative. Times 9.8 times 2 equals 1/2 VF squared. Again, I am anticipating this number to be greater because he should speed up as he falls. So 1/2 times 5.1 squared plus 9.8 times 2. This side of the equation gives me 32.6 equals 1/2 VF squared. We're going to multiply each side by 2, and then we're going to square root it. So this gives me a final velocity of my person of 8.07. So you could just say 8 meters per second, which checks out. I sped up as I went down. Great. Now I'm going to remember that 8.07. I'm going to clear my screen real quick because we know at this moment he's going 8.07 meters per second. Because the next part says if the trampoline behaves like a spring constant 6.3 times 10 to the fourth, how far does he depress it? So we're going to kind of get a little trippy here because he's going to depress it, which means there's going to be a negative height. We're going to be negative. So there's some negative gravitational energy. So at the initial position, we have all kinetic energy because he's moving. And then the final position, we've got some spring energy and we have some gravitational energy because since he's below that 0 point, there's actually negative gravitational energy. This is getting really nitpicky here. So the kinetic energy is going to be 1/2 mv squared. And then we've got equals, sorry, can't erase. So equals 1/2 kx squared plus, not 1, mgh. Now this h, the height, is actually going to be the negative x here. So I'm going to revise this. So 1/2 mv squared equals 1/2 kx squared minus mgx. Because since we have that height, how far I go below is also how far the spring is going to get stretched. And we want to know how far does he depress it. So we got a little bit of work to do here. So 1/2, our mass was 66. Now we can't cancel out the mass this time because there's no mass in that spring value. Times 0.87 squared equals 1/2. 6.3 times 10 to the third, fourth, whoops. And we're going to square that, minus 66 times 9.8 times x. So let's plug this all in and get some values. We're going to have to do a little bit of, wait, I messed this up. X squared, my bad. We're going to have to do a little bit of quadratic formula here. So 0.5 times 66 times 0.08 squared. This gives me 2,149.1. 1/2 times 6.3 times 10 to the fourth. This gives me 31,500. And then we still have that x squared there. Minus 66 times 9.8, which gives us 646.8x. Now you might be like, Ms. Schulte, this still doesn't look like a quadratic formula. I'm going to move this to the other side. So we have 0 equals 31,500 x squared minus 646.8x minus, is that 2,149.1. Now, does it look like a quadratic formula? We've got a squared x, a not squared x, and a thing. So I'm going to pause. I'll pause the video in a second, but you're welcome. You should know how to do the quadratic formula. The x equals negative b plus or minus square root b squared minus 4ac all over 2a. I want to encourage you to do this. I'm going to pause my video and do this calculation because this is an algebra 2 skill. It's not a physics skill, but I'm going to pause it, solve for x real quick, and then I'll unpause my recording. All right, if you did this calculation, you should have got a positive 0.27 and a negative 0.25. And I want you to think to yourself, which one's my correct answer? Because it's kind of hard to figure out. Now, thinking about this, we said that the up was my positive direction. So if I got a positive answer, that means my displacement was up 0.27. If I got a negative answer, that means my answer was down 0.25. So the correct answer for this one was negative 0.25, and then our units would be meters. So thinking about how big is that actually, it went down about this much between my fingers, which makes sense. Like if I'm jumping on a trampoline, I would expect to move, like that's a lot, but he's jumping off a box, so it's not that unrealistic. All right, I have one more example. If you feel good about this, you're welcome to stop watching at this point. This next one is really just, I'm going to show you the problem. I'm going to pause the video, encourage you to try it, and then I'm going to show you the answers. So I've got a situation of a roller coaster. I've got 4 different points. I'm giving you some total energies and some values. I want you to pause, see if you can calculate this on your own, and then when you come back, then I want you to stop and see if you can figure this out. Check your answers. So right now, pause the video. All right, I'm back. Please take a look at these answers. Really what I want to point out, the total energy is staying constant the whole way through. Anytime I needed to calculate my gravitational energy, either if I had a value, I subtracted that from my total energy, or I was using the MGH equation. So like for here, I used MGH. gave me my mass. For here, I used mgh, and here I used 1/2 mv squared. Other than that, a lot of the times, like for this dissipated energy, I just took the idea that my total energy would be my gravitational minus my kinetic. If this is a challenge, please come talk to me. Please do extra practice. Everyone has mastering physics to do now, so let me know if you have any questions.